Have you ever pondered the nature of space and time? Consider this. What if the length of an object changed depending on how fast it was moving? This isn't a riddle or a trick question, it's a fundamental concept in physics known as length contraction. In the early 20th century, a certain Mr. Albert Einstein proposed a revolutionary theory, the theory of special relativity. One of the most fascinating aspects of this theory is the concept of length contraction. But what exactly is it? Imagine a spaceship zooming past you at a speed close to the speed of light. According to Einstein's theory, if you were to measure the spaceship's length as it whizzes by, you would find it to be shorter than its actual length. Yes, you heard that right, shorter. This apparent reduction in length is what we call length contraction. Now, you might be wondering, how does this happen? The answer lies in the relativity of measurement. If you were on the spaceship, stationary relative to it, you would measure its proper length, the real intrinsic length of the spaceship. However, as an observer watching the spaceship fly by at near light speed, you would measure a shorter length. This is because the length of an object is relative to the observer's frame of reference. But don't get too excited about trying to measure this at home. Length contraction only becomes noticeable when objects are moving at speeds close to the speed of light, a speed that is nearly impossible to achieve with current technology. So how do we know how much an object will contract? Well, thanks to the Lorentz transformation equations, which were derived from Einstein's theory of special relativity, we can calculate the degree of length contraction based on the relative velocity between the object and the observer. The concept of length contraction has profound implications for our understanding of space and time. It tells us that space and time are not separate entities but interconnected aspects of a four-dimensional space-time continuum. It also highlights the importance of reference frames in physical measurements, reminding us that the universe is not as absolute as it might seem. So, the next time you look up at the stars and see a spaceship zooming past, remember that it's not just moving, it's also shrinking, at least from your perspective. And that, my friends, is the magic of length contraction, a cornerstone of Einstein's special relativity.